The next chapter is chapter 5, work, energy and power. In this chapter we will learn about doing work, transferring energy, work done equals energy transferred, gravitational potential energy, kinetic energy, GPE, that is gravitational potential energy, kinetic energy transfers or transformations, up, down energy changes. That is when something moves or slides down and then goes up. So you will have kinetic to potential, potential to kinetic energy transformations. Then you will see more energy transfers, efficiency, and the principle of conservation of energy. This is very important. Whatever is highlighted in green like this in this book is important. You have to memorize it with understanding, because in paper 2 or even paper 4 they can ask you to write it down. So if you try to write it in your own words, you might miss certain keywords and not score the full marks. Then over here we have seen this equation in the O-level class also. Power equals work done over time taken, and remember work done equals energy transferred. So we can even say power equals energy over time. Here power equals work over time. We can also say power equals energy over time, because work done equals energy transferred. Then we have this equation, work done equals force into distance moved in the direction of the force. And you know, distance moved in the direction of the force, that is displacement, and displacement is velocity times time. So we can write this equation, W equals F into ds, W equals F into V into T. Then power equals work over time, and we can write this equation here, because work is this, so we write that, and then V over T, and T and T can cancel, so you get power equals force times velocity. So this is another important equation. There are examples and you can see the key points or summary here. This equation is important. Remember, we saw this equation just now, equation for kinetic energy and also the equation for potential energy you have learned in the O-level class. Work done equals pressure times change in volume. This is for a gas, okay, where the pressure is constant. We will see the details. Then work done is force into distance moved in the direction of the force, that is also the displacement of the force, and this angle theta is the angle between the force vector and the displacement vector. We will see the details. So let's go to the beginning. Chapter 5, work, energy and power, learning outcomes. You should be able to give examples of conservations of energy between different forms, conversions or transfer of energy from one form to another form. The more appropriate word is transfer instead of transform, but in this book you will see the words transform used. The best word to use is transfer of energy. Understand and use the concept of work. Remember, work done equals force into distance moved in the direction of the force, and work done equals energy transferred. You should know those. Apply the principle of conservation of energy to simple examples involving energy in different forms. Derive and use the formula for kinetic energy and potential energy. Define and use the equation for power. Okay, so here you can see doing work, transferring energy. When this person lifts this weight, the person is doing work to increase the gravitational potential energy of this weight. So what happens is, chemical potential energy in his body is converting to gravitational potential energy in the weights. The weightlifter shown in figure 5.3 has powerful muscles. They can provide the force needed to lift a large weight above her head, about 2 meters above the ground. The force exerted by the weightlifter transfers energy from her to the weights. We know that the weights have gained energy because when the athlete releases them, they come crashing down to the ground. It's hard to work being a weightlifter. It's hard work being a weightlifter. Okay. So remember, for work to be done, a force has to move something a certain distance. If the force is applied so that the object doesn't move, then no work is done. And if the force vector and the displacement are perpendicular to each other, then again no work is done. So this equation we can also write as F cross S or F times S cosine the angle between these two vectors. So I will write it and show you. Now, yeah, so this is what I explained. In fact, if you want to know the scientific meaning of the word energy, we have to say it is that which is transferred when a force moves through a distance. So work and energy are two closely linked concepts. Now I told you, I think it's also here, work done equals energy transfer. You should know that. Okay, then in fact, if you want to know the scientific meaning of so work and energy, okay, in physics we often use an everyday word but with a special meaning. Work is an example of this. Table 5.1 describes some situations which illustrate the meaning of doing work in physics. It is important to appreciate that our bodies sometimes mislead us. If you hold a heavy weight above your head for some time, your muscles will get tired. However, now if that object is stationary, even if there is a force holding it up, no work is done, because for work to be done, the force should move the object a certain distance. So that is what it is explained. See, however, you are not doing any work on the weights because you are not transferring energy to the weights once they are above your head. Your muscles get tired because they are constantly relaxing and contracting, and this uses energy, but none of this energy is being transferred to the weights. See, doing work, not doing work. Pushing a car to start it moving, your force transfers energy to the car's kinetic energy, that is movement energy, increases. Kinetic energy is also called movement energy. And not doing work, pushing a car but it does not budge. Like I said, if it doesn't move, no work is done. No energy is transferred because your force does not move it. The car's kinetic energy does not change. Then again, lifting weights also, I already explained this. Okay, so if it moves, yes, then work is done. If you're just holding it at the top of your head such that it doesn't move, then no work is done. A falling stone, the force of gravity is doing work. The stone's kinetic energy is increasing. When the stone falls, its height from the ground decreases. So the gravitational potential energy decreases because gravitational potential energy equals mgh. Now if h, the vertical height, that is from the ground to the center of mass of the object, is decreasing, the gravitational potential energy is decreasing. So the weight is doing work to increase the kinetic energy, because it is the weight force that moves the stone towards the earth. Then moon orbiting the earth. Now the moon orbits the earth at a constant height, and the weight force is perpendicular to the direction the moon orbits the earth. So the weight force of the moon due to the earth, or we can say the gravitational force of the earth on the moon, is towards the center of the earth, and the moon is orbiting the earth perpendicular to the direction of the force. So therefore no work is done, because that angle between the displacement and the direction of the force is 90 degrees. So if you take the cosine of 90, that is 0. So remember the equation, it's also here in the summary. I will show you this equation. Okay, so the angle theta is the angle between the force and the displacement. If this angle is 90 degrees, then W equals Fs. Sorry, Fs times 0. Cosine 90 is 0. If the angle between them is 0, that means both are in the same direction, then this angle is 0. So cosine 0 is 1. Okay. Then writing an essay, you are doing work because you need to a force to move your pen across the page or to press the keys on the keyboard. Reading an essay, this may seem like hard work, but no force is involved, so you are not doing any work. Okay, I think that is easy to understand. Then calculating work done, remember this is the important equation. You can also write it as W equals F into S or W equals F into S cosine theta, where theta is the angle between the force F and the displacement S. The work done by a force is defined as the product of the force and the distance moved in the direction of the force. This part is important. You have to say distance moved in the direction of the force or the displacement of the force, where S is the distance moved in the direction of the force. Now here is an example to help you understand this better. He is applying a force in the direction the car moves. The force applied is 300 newtons. The displacement S is 5. So the work done is 300 into 5, which is 1500 joules. Energy transferred, work done equals energy transferred. Then from this equation over here for work done, you can see the unit of force is newtons, the unit of displacement is meters. So then we get Newton meter. Newton meter is joule here. So 1 joule is the work done when a force of 1 Newton moves an object a distance of 1 meter. So that is what we have here. All what you see in these green boxes are very important. You have to memorize them with understanding. So that is mentioned here, that what I explained just now. Okay, you have to answer all these questions and check the answers in the last few pages or the CD-ROM of this textbook. The solutions are there. That will ensure that you understood this content well. Okay, next, force, distance and direction, and this is what I explained. Okay, so you can go through this for more information. Now some more examples of doing work and not doing work. I think I already explained this about the moon and the earth, but here you have an artificial satellite. Artificial satellite is a man-made satellite like the Hubble Space Telescope. Moon is a natural satellite because it is made by nature. So here you can see the weight force is always directed towards the center of the earth, the weight force on the satellite, and the satellite is moving at an angle that is at 90 degrees to that. So the weight force is like the radius of a circle, and this is like the circumference of the circle. Remember, circumference and radius are always perpendicular to each other. So here work is done, here also work is done, but in the third column no work is done. Okay, here the work done is F into that vertical height which it falls by. Now for example, here you drop a stone weighing 5 newtons from the top of a 50-meter high cliff. What is the work done by the force of gravity? Force on the stone F equals the pull of gravity, that is the weight of the stone, or the gravitational force on the stone due to the earth. That is 5 newtons vertically downwards. Now what is the height? Distance moved by the stone is 50 meters vertically downwards. Therefore the work done is equal to F into S, which is 5 into 50. 250 joules. Now what about this? Again remember, it should be the distance moved in the direction of the force. That's why we use cosine of the angle between the force and the distance moved in the direction of the force. Now here the angle theta is 0, so cosine 0, that is 1. But here the angle is not 0. The weight force is this way, the distance is this way that it moves. But if you take the component of this distance in this direction, which is in the direction of the force, then you can simply multiply F times 30. That will give you the answer. Now you can also try something like this. Now if you know this angle here, remember this is a 3, 4, 5 Pythagorean triple, 30, 40, 50. Remember 3, 4, 5. Similarly, if this side is 30, this side is 50, that means here it is 40 meters. So 3, 4, 5. Now here the angle then is 60 degrees, right? Yeah, we can actually check that. Now remember, if both this side and this side are equal, then the angle is 45 degrees. So we can try, anyway they have also given us, so 50 cosine of the angle here. Okay, so a cosine 60 is half, so yeah, it's not that case, right? Anyway, if we know this angle, then 50 cosine of this angle should give you this side, but we don't know what this angle is right now. But anyway, they have given this side, so let's do this. A stone weighing 5 newtons rolls 50 meters down a slope. What is the work done by the force of gravity? Force on stone F equals the pull of gravity. Weight of stone, which is equal to the weight of the stone, and again remember 5 Newton weight. Distance moved by the stone down the slope is 50 meters, but the distance moved in the direction of the force is 30. So the work done is 5 times the weight of this times this, 30, 150 joules. Okay, here no work is done because the force and the distance moved are perpendicular to each other, which means the angle is 90, so cosine 90 is 0. So no work is done. See, so here you have the force F, angle theta, and this is the distance moved in the direction. This is it's moving in this direction, so it's F cosine theta. So if you want the force in the direction that it is moving, or even you can resolve the distance in the direction of the force, either way you will get the same answer. Or simply you can say it's F times S and cosine of the angle between the two vectors F and S respectively. Okay, let's go through an example to help you all understand this better. A man pulls a box along a horizontal ground using a rope. See that? He's moving this way, and the object is also moving in the horizontal direction, but the force is applied that way. Now look, the distance moved is 5 meters. The angle between the force and the distance moved is 30. So it will be what? 200 times 5 times cosine of 30, because we are using this equation. The work done is Fs cosine theta. Okay, where theta is the angle between the force F and the distance moved S, like this. So simple, 200 times 5 times cosine 30. So what they do is they resolve this force in this direction, which is 200 cosine 30, and then they multiply it by 5. Or simply you can use this equation directly. That will avoid any confusion. Okay, then you get 865. Now another important topic is a work done by a gas doing work, in other words. So this is very important. I have seen past paper questions based on this, and sometimes students have forgotten that they learned this. Now over here the change in volume is the area of cross section times this, because remember this is like a prism, it's cylindrical in shape. So the area of a prism is an object with a uniform cross section along its length, so it will be A times S. Okay, area of cross section times S will give you the volume here. Okay, so F equals pressure times area. You have learned this already. The equation for pressure is force times area, then force is pressure times area. The work done is equal to the force times the distance moved in the direction of the force, which we call the displacement. So we have that equation, W equals Fs, remember, and F here is the pressure times the area. So then we get area times the cross-sectional area times S, that is the volume here. Okay, so delta V, the change in the volume. So work done equals P times delta V. Then this equation is important. Now remember, like I mentioned in the beginning of the lesson, the pressure P does not change as the gas expands. So it's a uniform pressure. Now for example, if this side is open to the atmosphere, the pressure here and the pressure outside will be the same, which is the atmospheric pressure. So this is the work done on a gas or by a gas at constant pressure. This equation is important. And remember that volume change is the area of cross section times S, which is similar to the area of a prism. Okay, then these questions are based on what we learned just now. Make sure you do these questions and check the solutions in the last few pages of the book or in the CD. Next topic is gravitational potential energy. You have learned this equation, gravitational potential energy equals mgh, in the O-level class. Now remember, this h is always a vertical height. It is from the reference level to the center of gravity of the object. That is the height h. It's the vertical height from the reference level, usually it is the ground, to the center of gravity of the object. Okay, so here we have a weightlifter raises weights with a mass of 200 kilograms from the ground to a height of 1.5 meters. Calculate how much work he does. By how much does the GPE of the weights increase? So you can use the equation W equals F into D. Work done is force into distance moved in the direction of the force. The force applied is equal to the weight of this. So here you can see the weight of this is mg, that is 200 times g, that is the weight. Now the distance moved is 1.5 meters, see, height of 1.5. So that is what we get. Now we can also use the equation. Now what is happening here is the work done is used to increase the gravitational potential energy of this. Now if you use the equation for gravitational potential energy, that is mgh, you still get the same result. mg is 200 into 9.8, h is 1.5. Okay, so work is done to increase the gravitational potential energy of the weights that is holding here. Okay, so this is how you get that equation. So from this equation, work done is force into distance moved in the direction of the force. We can get the gravitational potential energy. The force applied is equal to the weight. The distance moved is the vertical height. We have other forms of potential energy also, such as elastic potential energy, chemical potential energy, nuclear potential energy. There are about 5 different types of potential energies. Elastic potential energy is also called strain energy. Okay, then we have nuclear potential energy, chemical potential energy, we simply say chemical energy. Electric potential energy. Potential energy is the energy an object has because of its position or shape. For example, an object's gravitational potential energy changes when it moves through a gravitational field. There is much more about gravitational fields in chapter 18. We can identify other forms of potential energy. An electrically charged object has electric potential energy when it is placed in an electric field. So if you have an electrically charged object, that means you have a charged particle in an electric field, that charged particle will move towards the oppositely charged plate, because unlike charges attract. So that's why, because when released it can move, it can do work, we say it has electric potential energy when it is placed in an electric field. An object may have elastic potential energy when it is stretched, squashed or twisted. Elastic potential energy is also called strain energy. If it is released, it goes back to its original shape. So you can see, due to it being stretched, squashed or twisted, due to the change in shape. Remember what we learned here, potential energy is the energy an object has because of its position or shape. Okay, now you have to answer these questions and check the answers in the last few pages of the book. That should be about what we learned just now about gravitational potential energy. Now the next topic is kinetic energy. Now in the O-level class also you have learned about kinetic energy. You have learned just one equation for kinetic energy, that is half mv squared. Again you can see this is in the yellow box. Even that equation for gravitational potential energy is important, you should know that. For an object of mass m traveling with speed v, we have kinetic energy equals half mv squared. This is the equation. Then how do we get this equation? Previously we have learned the equations of motion for uniform acceleration. Remember we learned about 4 or 5 equations. So using those equations we can get this equation. Let's see how we can do it. We have learned this equation, v squared equals u squared plus 2as. So if an object starts from rest, the initial speed is 0. Then we get this equation. Now we can multiply both sides of this equation by half m. So we get half mv squared equals mas. Now what is ma? That is the force. Remember Newton's second law, F equals ma, and s is the distance moved in the direction of the force. So the force is doing work to increase the gravitational, the kinetic energy of the object. Now imagine there is a stationary car. When you turn it on and accelerate, there is a resultant force on the car, that is ma. Remember, resultant force is m times a, and s is the distance moved in the direction of that force. So we have half mv squared, that is the kinetic energy, equals Fs, which is mas. Now the work done is used to increase the kinetic energy of that object. That's why its speed increases. Then we have this equation. So that's how we get the equation for kinetic energy. This is the energy transferred to the car, and hence its kinetic energy. That's why its speed increases. Kinetic energy is also called movement energy. If the speed increases, that means the kinetic energy increases. Now here we have gravitational potential energy, kinetic energy transformations. So if you look at the diagram, you can see over here. So for it to go from here to here, the engine has to do work to raise it up here. And what is it doing work? It is doing work to increase the gravitational potential energy of this roller coaster. Now when it passes that highest point where it has maximum kinetic energy, because it is at the highest point, it can simply come down like this, because here it has gravitational potential energy. Now when it comes somewhere here, due to gravity, it will be pulled down. So the height decreases. When the vertical height decreases, the gravitational potential energy decreases and the kinetic energy increases. That's why the speed increases when it goes down. Then here at the lowest position, it has maximum kinetic energy and zero potential energy. So here we can say, if there was no friction, all the gravitational potential energy here converted to kinetic energy here, assuming there is no frictional forces. Then what happens? When it goes up, the kinetic energy decreases and the gravitational potential energy increases, because its speed decreases. So when the speed decreases, kinetic energy, also called movement energy, decreases. That means something else should increase, because of the law of conservation of energy, or principle of conservation of energy, which states that energy cannot be created or destroyed, but it can be transferred from one form to another. And that is what is happening here. Kinetic energy is converting to gravitational potential energy. There is another example here. When the pendulum moves back and forth, its speed increases and decreases. So here the speed is 0, here also the speed is 0 at the highest points, and they reverse direction. So when the speed is 0, the kinetic energy is 0. That means here it has only, at the highest points, it has only gravitational potential energy. Now at the lowest point, because we are taking the gravitational potential energy with reference to this level, the lowest level, at the lowest level, the gravitational potential energy is 0. That means it will have maximum kinetic energy. Now you can see that here, when it goes from here to here, the speed here is 0, speed increases, reaches a maximum value, and then the speed decreases to 0 here. Okay, so here you can see the example is asking us to calculate that, right? And by the way, if we go through this over here, these key points, the roller coaster car accelerates as it comes downhill. It's even more exciting if it runs through water. As the car runs along the roller coaster track, figure 5.13, its energy changes. At the top of the hill, it has the most GPE, gravitational potential energy. As it runs downhill, its GPE decreases to kinetic energy, decreases, and its kinetic energy increases. I already explained all those here. At the bottom of the hill, all of its GPE has changed to kinetic energy and heat and sound. Okay, so here there is friction. So the gravitational potential energy here has converted to kinetic energy, and on the way, due to friction, there is thermal energy produced, and also there is sound energy produced. At the bottom of the hill, all of its GPE, gravitational potential energy, has changed to kinetic energy and heat and sound energy. As it runs back uphill, the force of gravity slows it down. Okay. kinetic energy is being changed to GPE. There are many situations where an object's energy changes between gravitational potential energy and kinetic energy. For example, a high diver falling towards the water. GPE changes to K because his height is decreasing, and when he falls, his speed increases. A ball is thrown upwards. When the ball is thrown upwards, what happens? The speed of the ball as it goes up decreases, and the height increases, so the kinetic energy decreases, and the GPE, gravitational potential energy, in other words, increases. A child on a swing, energy changes back and forth between GPE and K. So here you can see the vertical height increases, decreases, increases, decreases. A pendulum consists of a brass sphere of mass 5 kilograms hanging from a strong string. See figure 5.14. The sphere is pulled to the side so that it is 0.15 meters above its lowest position. You can see that in the diagram. It is then released. How fast will it be moving when it passes through the lowest point along its path? Okay, first we can find the gravitational potential energy here. That will be equal to the kinetic energy here, assuming there is no friction. So the gravitational potential energy here is mgh, and we don't even need to find the gravitational potential energy. We can set the gravitational potential energy here equals the kinetic energy there. Then you can see the mgh and equals half mv square. The m's are there on both sides of the equation, so it cancels out. We'll see. I think yes, the working is shown here. See, yeah, we don't even need this because the m's cancel, but if you want, yeah, okay, that is what is shown here. If you want, otherwise we can find the gravitational potential energy here, because mgh, all three are given, and then that is equal to the kinetic energy. We set them like that and find the v. Okay, finally, energy transfers. The efficiency equation was also introduced in the O-level class. Efficiency equals useful output energy divided by total input energy times 100%. 100% if you want to write it as a percentage. Now remember, work done equals energy transferred. So we saw a second equation, that is the useful work done divided by total energy input. Okay, so we had a third equation also. Now if you divide both numerator and denominator by time, we get useful output power, because energy over time is power. So useful output power divided by total input power. If you divide both numerator and denominator by the same quantity time, you get power here, power there also. Okay, this is called a Sankey diagram because the width of the arrow is proportional to the amount of energy. You can see here, let's say this is 10 centimeters, then this width will be 8, this will be 2 centimeters. Chemical energy supplied to engine, heat to the environment, kinetic energy to the wheels. So you can see majority of the energy is wasted. So with this we can even find the efficiency. Efficiency is useful energy output divided by total energy input into 100%. So that will give us 20% efficiency. Okay, conservation of energy. This is the principle of conservation of energy. It's important. You have to memorize it with understanding. In the exam papers, paper 2 or even paper 4, the theory papers, they can ask you to write down this principle. If you try to write it in your own words and if you miss certain keywords, you would not get the full marks. Okay, let's see. Energy cannot be created or destroyed. It can only be converted. The better word is transferred from one form to another. So the total amount of energy in the beginning, we should always be able to add up the total amount of energy at the beginning and be able to account for it all at the end. We cannot be sure that this is always the case, but we expect it to hold true. We have to think about energy changes within a closed system. That is, we have to draw an imaginary boundary around all the interacting objects which are involved in an energy transfer. Okay, so here is an example. Let's see. Figure 5.17 shows a dam which stores water. The outlet of the dam is 20 meters below the surface of the water. It's indicated in the diagram. In the reservoir, water leaving the dam is moving at 16 meters per second. Calculate the percentage of the gravitational potential energy that is lost when converted into kinetic energy. Water stored behind the dam has gravitational potential energy. The fast flowing water leaving the foot of the dam has kinetic energy. We will picture 1 kilogram of water starting at the surface of the lake where it has GPE but no KE. K is kinetic energy, GP is gravitational potential energy, and flowing downwards out at the foot where it has kinetic energy but less GPE. Then change in the gravitational potential energy of water between surface and outflow, that is mgh. So from here to here, mgh, m, that is if we assume for just 1 kilogram of water, okay, g is 9.8, h is 20 meters. Then again we can assume that same 1 kilogram is leaving from here. Okay, so it comes down, it leaves from here, and when it is leaving, it has a speed of 16 meters per second. Now we will find the kinetic energy over here. That is again half mv squared. M is 1, v is, so you have 128 joules of kinetic energy, 196 joules of original energy here, which is the gravitational potential energy. Now if there was no energy loss, then the number here, the kinetic energy here, should be equal to the gravitational potential energy there, but it is not the same. So the difference in the energy is the energy lost due to heat, due to other factors, due to friction. For each kilogram of water flowing out of the dam, the loss of energy is 68 joules. So 68 divided by, now this is not the efficiency, we are finding the percentage loss here. If you want to find the efficiency, that will be 128 divided by 196 into 100%, because it's useful energy output divided by total energy input into 100%. But here we are finding the percentage loss. Percentage loss is what? The difference between these two values, that is 68 joules divided by the original into 100%. So that is 35% loss. If you wanted to use this moving water to generate electricity, you would have already lost more than a third of the energy which is stored when it is behind the dam. So here original amount of energy is this. So if you take 1/3 of that, you can see that here it has lost more than 1/3 of the energy which it stores when it is behind the dam. Alright. Yeah, so this part is under radioactivity. Okay, later you will see in the radioactivity chapter about the neutrino. Okay, you have beta minus decay and beta plus decay. In those decays you have neutrino and antineutrino. So here you can see, although we cannot prove the energy, that energy is always conserved, this example shows that the principle of conservation of energy can be a powerful tool in helping us to understand what is going on in nature, and that it can help us to make fruitful predictions about the future. Okay, next topic is power. You have seen this equation, power equals work done over time taken. We can also say power equals energy transferred, because work done equals energy transferred. We saw it previously. So power equals W over T and power equals E over T. W is for work done, E is for energy transferred. Unit of power is watt. Joules per second is watt. See, it's shown here. And about bulbs, 60 watt, 10 watt. Okay, you have to answer these questions and check the answers in the CD. Next example, the motor of the lift shown in figure 5.18, that is this one. A lift needs a powerful motor to raise the car when it has a full load of people. The motor does many thousands of joules of work each second. Okay, provides 20 kilonewtons force. This force is enough to raise the lift by 18 meters in 10 seconds. Calculate the power output of the motor. Output power of the motor. So first we must calculate the work done. Work done is force into distance moved. Okay, so that is 20 kilonewtons times 18, right? 18 meters, yes. So we have this. Now we have the work done and we can find the power, because power equals work over time. And how soon does this happen? In 10 seconds. So we divide by this. All are in SI units. So here also, yeah, here it's already here in kilonewtons. Okay, so that's why we get this in kilojoules. Now here we have written it in joules. So we if we should be 36,000 watts, but they have again written it as 36 kilowatts. If you write this as 360 kilojoules, then that you can just keep the k there, kilo. Then joules per second is what? So this will be this zero goes 36 kilowatts. Take care not to confuse the two uses of the letter W. Watt, a unit. W again work done, a quantity. So the lift's motor's power is 36 kilowatts. Note that this is its mechanical power output. The motor cannot be 100% efficient, since some energy is bound to be wasted as heat due to friction. So the electrical power input must be more than 36 kilowatts. Okay, then the equation for power. Remember the equation for work done. Work done is force into distance, and I think I explained this earlier. Distance is speed times speed times time, and we have power equals work over time. Then work is this, so T cancels, you get this. Power equals force times velocity. This is a very important equation. You have to memorize it with understanding and be able to use it. Okay, so here are some explanations. We can go through you have to answer all these questions. Let's go through this example, the last example for this chapter. A person who weighs 500 newtons runs up a flight of stairs in 5 seconds. Figure 5.19. Their gain in height is 3.0 meters. Calculate the rate at which work is done against the force of gravity. 3 meters, weight is 500. So the work done is force into distance moved in the direction of the force. Now the distance moved in the direction of the weight force is 3 meters. So it's 500 times 3, which is 1500 joules. They are asking us the rate at which work is done. Power equals work over time. So this is the rate at which work is done. We are, in other words, supposed to find the power. So it's this divided by the time, which is 5 seconds. So we get 300 watts. So while the person is running up the stairs, they are doing work against gravity at a greater rate than their average power, perhaps 3 times as great. And since our muscles are not very efficient, they need to be supplied with energy even faster, perhaps at a rate of 1 kilowatt. This is why we cannot run upstairs all day without greatly increasing the amount we eat. The efficiency of our muscles also explains why we get hot when we exert ourselves. Okay, that's the end of the lesson. Now these key points or summary has all the important points. So this summary is very important. Let's go through what we have learned just now. The work done, W, when a force F moves through a displacement S is in the direction of the force, is W equals Fs. Now if F and S are both in the same direction, then we can simply use this equation. Now if they are at an angle to each other, now here the angle is 0, so cosine 0 is 1. Now even if you look at this equation, the angle theta is the angle between the force F and the displacement S. So if theta is 0, then you get this equation. Now if theta is 180, you get minus Fs. The force and the distance are in opposite directions. Then if this angle is 90, the force and S are perpendicular to each other. Cosine 90 is 0, so no work is done. Where theta is the angle between the force and the displacement. Then we learned what joule is. A joule is defined as the work done or energy transferred when a force of 1 Newton moves an object a distance of 1 meter in the direction of the force. So this is for 1 joule. Okay. The work done W by a gas at pressure P when it expands. Remember, this happens at constant pressure. We saw the example of the piston. Remember the syringe? There was a diagram I told you that is very important. There have been questions on this in the past papers, and a lot of students would have probably forgotten the theory because this is under a small section in this chapter. Okay, so anyway, this is the equation. I showed you how to derive it also, where delta V is the increase in its volume. When an object of mass m rises through a height h, its gravitational potential energy EP increases by an amount. So P is for potential, E is for energy. So this potential energy. And remember, this h is a vertical height from the reference level, which is usually the ground, and that is the vertical height from that reference level to the center of gravity of the object. So remember, very important. Then we saw the equation for kinetic energy. You have learned this in the O-level class also. The kinetic energy Ek of a body of mass m moving at speed v is this. The principle of conservation of energy states that for a closed system, remember, some students forget to write this. So you have to say closed system. Otherwise, you might miss the point for the answer. If they ask you to write the definition, you have to write all of this. The principle of conservation of energy states that for a closed system, energy can be transformed to other forms. You can say transferred. But the total amount of energy remains constant. The efficiency of a device or system is determined using the equation. Power is the rate at which work is done or energy is transferred. What is defined as a rate of transfer of energy of 1 joule per second. So we saw this. What is joules per second? Remember, from the equation, P equals W over T. So this is in joules, this is in seconds, so this will be in watts. Now power, also we learnt a second equation. You would not have seen this in the O-level class. We saw power equals force times velocity. Okay, so this is also important. What is defined as a rate of transfer of energy of 1 joule per second. Okay, so that's the end of this lesson. Make sure you answer all these questions in the brown boxes. These are called the self-assessment questions that will check whether you understood the theory throughout each part of the chapter. Then once you finish all that, check the work, and once you have understood everything, make sure you do these end of chapter questions and check the solutions for that also. It's also in the CD in the last few pages of this book. And the key points are here. These are also very important. So you have to know these equations. This one, equation for work done, the definition for work done, what is a joule, what is the work done by a gas at, again you can write here, constant pressure when it expands or contracts. Okay, where delta is the increase in its volume or change in its volume. If the gas is expanding, work is done by the gas. If the gas is contracting, work is done on the gas. Then the equation for gravitational potential energy, equation for kinetic energy. Kinetic energy is also called movement energy. So an object should have a mass and it should be moving for it to have kinetic energy. We saw the principle of conservation of energy. This definition is important. We saw the equation for efficiency, and I told you 2 more equations which you had learned in the O-level class. Because work done equals energy transferred, we can say useful work done divided by total energy input. And if you divide both numerator and denominator by time, this will become power. Useful output power divided by total input power. Okay, so then we have this equation, and we saw we learned what a watt is. We have 2 equations for power here. Okay, so answer these questions after answering the self-assessment questions and checking each solution. And the next topic is chapter 6, momentum. Okay, so this is the end of this lesson. Now if you look at the links in the video description, you can have access to our complete online course. The complete Cambridge AS and A-level physics course is available online. Anyone who has an internet connection, if any of you all are watching this video, that means you all have an internet connection, and that is sufficient for you all to follow this online complete Cambridge AS and A-level physics course. So this is everything you need for you to get an A-star grade for your exams. So many students have taken our online classes and in a matter of a few months they have gone from C and D grade students to A and A-star students, and even won prizes from Cambridge. You can see the testimonials on our website. By the way, this online course has these lessons, theory lessons recorded along with the notes. Then there are tutorials which you can watch the video explaining each question in the tutorial, and finally you can watch the past exam paper questions. Each question in the past exam papers are explained. You can even download the solved exam paper if you want. So that will, you can also join our live online classes. So if you have any doubts, then you can join a live class like this from any part of the world and get all your questions answered. For more information, check the links in the video description. We also have other online courses like O-level physics, A-level mathematics, O-level mathematics. You can also join our online classes without purchasing the complete course. So for that also you can see the information in the video description, and I hope to see you all soon in an online class.